my name is Sohaila.
Hi, I'm Jack,
Hey, I'm Mart.
Hi, I'm Brian.
Hi, I'm Maddie.
and we are Voithos Drones. We'll be presenting you today with our new tool, the Rock Climbing Assistant. I hope you enjoyed this presentation.
Rock climbers often need to go out with a partner and follow strict guidelines and paths established by the National Park Service. Voithos is aimed to create a drone that gives climbers the confidence and ability to climb without a partner, giving them more mobility and freedom. This drone will use topographical data to determine safe or ideal paths for the user, and will monitor them while they climb as a safety precaution. If the climber falls or is otherwise injured, the drone will send an emergency signal to the National Park Service. There's not necessarily a constraint on this project, but we are operating under the assumption that all technology needs that we have to create the drone are achievable within the project lifecycle. The drone has three main functional branches. The first is mapping, the second monitoring, and the third is in the case of an emergency. The first functional branch proceeds as shown. First, the drone will locate the rock climber so it establishes a reference point. Next, it surveys the mountainside, recording images. While it is recording, it begins to process the data it has received from the images and compares it to the topography of the area. It searches for paths for the climber to take, as well as possible landing locations for the drone in the event of an emergency. After the data has all been processed, it presents the options to the user via a Bluetooth connection to a phone app and awaits user input. After the user chooses a path and begins climbing, the drone follows the second functional branch. The drone follows the user, awaiting either input via the app or a rapid change in position or acceleration measured by the phone's accelerometer. If a person has a smartwatch, they compare it with their phone and with the application to give the drone access to the user's vitals. The drone will stay in this functional branch for the longest period of time. Based on the information collected by the drone through the phone app, it will then make a decision on whether or not to move on to the third functional branch. If the drone detects a rapid change in position or acceleration by the climber, or a sudden change in their vitals, it will enter this third branch. The drone will first attempt to contact the user via the phone app. If the climber does not respond on the app within a period of 1 minute after the sudden change, then the drone will determine the coordinates of the climber using the phone's GPS, then send an emergency signal to the National Park Service. After the signal has been sent, the drone will land and all power allocation will go towards the refreshing of that signal. If the user does respond on the app, however, the drone will return to a standby mode, from which a return to climb can be established, or the drone can be powered off.
The life cycle of this project begins with pre-phase A by defining the mission's needs, goals, and objectives, along with identifying stakeholders and developing a concept of operations. We decided that pre-phase A up until phase C should all be completed within a year. Phase A includes performing trade studies to justify design decisions and developing a baseline mission concept for our drone. Phase B includes establishing our initial design, developing a prototype, and test and evaluation to demonstrate our technology development is complete. This leads to Phase C by when we have a final design and begin the manufacturing process, along with marketing our product to interested consumers. By Phase D, we get into year 2 of the project lifecycle and begin launching and delivering purchased drones. Phase E spans into year 4, by which we are growing the business, doing further R&D, for example, new accessories, software updates, and longer battery life, and expanding into new markets. Finally, Phase F includes future years to come, by which we hope to see our drone being used all over the world and have established a footprint in the drone market. The work breakdown structure includes the components of the product breakdown structure, along with the hierarchical decomposition of the work to be carried out by the team to accomplish the project and create deliverables. For our drone, the project breakdown structure is comprised of the components that made up each of our 5 subsystems. The first main area of project division is management, which comprises of marketing, including promoting, advertising, and selling the drone. It also includes HR, which deals with hiring, administration, and training of personnel in our company. Finally, it includes operations and supply chain, which oversees the conversion of raw material, labor, and capital into a final product or service. The second area of product division is systems engineering, which includes systems integration. This is the process of bringing together component subsystems into a whole and ensuring that those subsystems can function properly together. The third area of project division is manufacturing. This includes CNC, which uses automatic machining to create parts, and assembly, which comprises of putting together all the parts to create the final product. This also includes distribution involving packaging, inventory, warehousing, and other logistics.
Our product is a beauty, essentially made out of 5 subsystems which all incorporate different and similar components that have been chosen to work together. Because of its nature, we do not have completely independent subsystems, as the red arrow shows in the schematic diagram here. Any changes made in one of the subsystems need to be carefully made, as it could have a positive or negative impact on the others, which is why we took care of including the diagram. Our propulsion, communication, imaging, and control subsystems are tightly coupled. Each of their name is self-explanatory, since they explain their main function in the product. The brain is essentially the flight controller, which has to send inputs to the ESC in order to enable the motor to function. The camera needs to know when to and when not to take pictures during the flight, but it cannot do that on its own. This means that coordination between the imaging and control subsystem is required. Also, once pictures are taken, they need to be available to the user via his or her smartphone to look at their climbing route, and that means that there is an interaction between the communication and imaging subsystems. GPS is needed to know the climber's position in case of an emergency. It is also needed to make sure that the drone is not flying too far away, thus the control and communication interface. Although our structure subsystem does not have a direct component interaction with the other subsystems, it is necessary to enable their altogether integration into one system.
These are the high-level system requirements for our quadcopter drone. Among them are that the drone shall comply with FAA guidelines, and the drone shall fly autonomously while remaining within 10 feet of the user. This means the drone will be flying or hovering near the user and will follow the user as he or she climbs. The drone shall fly for a minimum of 1 hour. While this is something we plan on working to extend to accommodate longer climbs, our drone will be able to fly for at least 1 hour. In addition, the drone shall also record video of the climber throughout the duration of the climb, allowing the climber to go back and watch the video to improve their climbing strategies or to share the experience with friends and family. The last requirement is that the drone shall alert authorities in the event of an emergency. It will do this if prompted by the climber or if the climber falls and is unresponsive. These are the margins and contingencies for our product. The current best estimate for the weight of the drone is 1,300 grams, and the maximum expected weight is 1,500 grams. The maximum possible value we decided on was 2,200 grams, which is about 5 pounds. We chose this because we want to ensure our drone is relatively light and can be easily carried by a rock climber for long distances. The current best estimate of power required is 90 watts, the max expected value is 115 watts, and the max possible value is 200 watts. To make sure our drone can fly for long periods of time, keeping the power consumption as low as possible is critically important. Our current best estimate for the cost of our product is $300, with a max expected value of $500 and a max possible value of $700. While our current estimate is to sell the drone at $300, setting the max possible value at $700 will keep our drone competitively priced compared to similar drones on the market. Our current estimate for the flight time is 2.5 hours, with a minimum expected time of 1 hour and a minimum possible time of 45 minutes, which, while not as long as we are aiming for, should still be long enough to accompany a rock climber on a basic climb.
We made the decision to go with a quadcopter because it presented an easy entrance into the market, had a reasonable flight time, and most of all, is a very dynamic, fast, and fun way to fly. We looked at alternatives in the flying space and arrived at a blimp-type system featuring a balloon and propellers. While it did increase the flight time considerably, as power is reduced drastically, it also limits the drone in its maneuverability and speed. This poses a direct counter to the dynamic experience we want our users to have. Next, we thought about systems that would not fly at all. The first was a drone that would roll on the ground and that would climb with the user. Again, this drone could potentially have a higher battery life and mission time, but the inability to get the bird's eye view image is a negative. Furthermore, this system would not necessarily work in all terrains, and hence it would limit our market options. Secondly, we thought the user could carry a panic button on their person. The panic button only would have the feature of alerting necessary authorities in the event of an emergency. It also comes with a very long battery life that is only limited by the phone. The drawbacks are too severe though, as they include no imaging and no interactive experience for the user. Lastly, we considered that the user could have no device other than an application on their smartphone. It would essentially work just like the panic button, but some cell phones are limited in capability in terms of communicating and operating power, as well as having the other drawbacks of the panic button. It would certainly be very cheap, but the experience of the user and the safety of the user are pivotal. At the current time, our drone has a technology readiness level of 3. We have established all the necessary systems, but we have not done any preliminary design, nor have we tested any components in the lab yet. Finally, we want our customers to come back again and again. The product obviously will be able to protect its components from a plethora of possible dangers. What we hope to do is make each component of the companion drone easily replaceable. In the future, we see our drone alongside a long line of products of the Voithos family. Each companion drone would be catered towards certain activities, opening new ventures of opportunities and communities to impact. Our goal is to create an essential tool for the everyday outdoor person, so I hope you choose to invest in us.